Hello guys, welcome back. The last data structure I would like to introduce in this unit is data frames. If you do data analysis in R, you will be using data frames. You can think of a data frame as R's equivalent to a spreadsheet or a database table, because it stores data in a rectangular form, as shown by this small example data frame. Data frames are the most useful storage structure for data analysis in base R. Internally, a data frame is a special list of named elements, each referring to a vector that stores individual values. We can easily draw an analogy between a column of a data frame and an element of a list. And thereby, a data frame can contain different types of data across different columns. But within a column, every value must have the same type. For example, the first column of this data frame contains only floating point numbers, while the third column contains only logical values. Compared with a regular list, a data frame has an additional constraint. That is, each of its underlying vectors must have the same length. As you can see, the three vectors contained in this data frame all have a length of 4. We can create a data frame from scratch with the data frame function by supplying any number of vectors, each separated with a comma. And we must ensure every vector has the same length. Otherwise, this function call will fail. Moreover, each vector should be paired with a name. In this code, I name these vectors income, gender, and default, respectively. The data frame function will turn each vector into a column of the resulting data frame, and these names will appear in the header of the resulting data frame to label the columns. If we had forgotten to assign a name to a vector, R could have given a weird name to the corresponding column. The resulting data frame stores a set of toy data and has a familiar tabular layout. Each row represents an observation or record, while each column represents a measurement or variable. A remark here regarding the use of the data frame function is that in practice, we seldom use the data frame function to create data frames because it involves typing large data sets by hand, and typing tends to invite typos and errors. If we want to perform data analysis in R, it is always better to create a data frame by importing data sets from an external file, as we will see in today's in-class exercise. The output of the class function prints the string data frame, indicating the object created in this way is a member of the data frame class. And calling the type of function returns the string list, which verifies that data frames are built on top of lists. Because a data frame is a list of equivalence vectors and has a two-dimensional structure, it shares properties of both the list and the matrix. These four examples show that many of the functions working for matrices can work with data frames as well. Please try them out in RStudio by yourself. We can also combine several data frames using column binding or row binding as we do with matrices. Column binding allows us to add more measurements or variables to describe our data, while row binding allows us to add more observations into our data sets. When data frames are combined column-wise, the number of rows must match, which means the length of the vectors supplied in the second data frame must be the same as that of vectors in the first data frame. When data frames are combined row-wise, both the number and names of columns must match. It means that the number of elements taken by the second data frame function must be the same as the number of columns in the first data frame. Moreover, these elements must be named the same as the columns of the first data frame. In other words, these keywords must conform to the names of these columns. You could also be interested in knowing the attributes a data frame has. Compared with a regular list, a data frame has two additional attributes, class and row names. And R is able to distinguish a data frame from a regular list because of these two attributes. As you can expect, these attributes can also be individually accessed by using the same name functions. Please try them out in RStudio by yourself. And the output of the structure function first shows the number of observations and the number of variables this data frame has. And it further tells us what vectors are wrapped within it, as well as their types. Notice that the gender colon contains a vector. Recall that we've passed a character vector rather than a vector to this colon when creating this data frame. So R actually converted the character vector as a vector automatically. Actually, many base R functions will do so, and vectors could be useful in this setting because it allows us to operate on categorical values easily. But if you want to store the character vector as it is, you can prevent this behavior by setting the string as vector keyword to false when calling the data frame function. As a result, the gender colon now contains the character vector. Next, I'm going to discuss how we can do subsetting and query with data frames. Because data frames are special lists, we can use the $sign indexing operator and the double bracket indexing operator to access a column of a data frame. And R will return all of the values in the column as a vector. With these two indexing operators, we can add new columns to a data frame. In the same way as we do with lists. But here we should make sure that new columns have the same number of rows as the existing data frame. So the vector on the right-hand side of the assignment should have 4 values. However, this type of subsetting or indexing only operates on columns. What if we want to query a data frame and filter rows? Because a data frame is also analogous to a matrix, we can query a data frame and filter its rows by taking advantage of the indexing possibilities for matrices using this notation. For example, if I would like to select all observations whose values in the default column are true, I can first construct a Boolean vector and then apply the Boolean vector to the index the row dimension using the indexing notation for matrices. Recall that the $sign indexing operator returns a vector of values, and this vector is then used in this comparison to form the criterion for row filtering. And there are two observations that satisfy this criterion, as shown by this output. If we want to further narrow in on a smaller set of observations, we can form a bit more complicated query with logical operators. But we have to type the name. We have to type the name of the data frame and the $sign for each criterion specified in this query, because we have to inform R of where to find the data. So it may involve a lot of typing, especially when the query is based on several columns. This query can help you see how cumbersome it could be. Fortunately, R provides a facility, this attach function, that can simplify the typing of these queries. Calling this attach function with the data frame enables its columns searchable by R without need to further refer to the data frame. Now we can use the column names directly to form complex queries. Here I also drop the default column by specifying an indexing vector for the column dimension, as all return rows will have true in that column. If we want to sort a data frame to present it in a better view, we can use the order function to sort rows of data frame by values in some column. However, the order function does not sort a data frame directly. Instead, it sorts a column and gives an output that can be used to select the rows of a data frame in order. For example, suppose we are going to sort the data frame by income in descending order from the largest income value to the smallest income value. Invoking the order function on the income column outputs this vector. It actually gives the positions of the largest value in the income column, and second, the position of the second largest value in the income column, so on until the position of the smallest income value in sequence. As you can verify, 4 is the position of the largest income value. 2 is that of the second largest income value. And 1 is the index of the smallest income value. So this vector gives a permutation of positions and tells us how to rearrange the income values into descending order. Setting decreasing option to true is necessary here, because otherwise the order function will output the reverse of this sequence that rearranges income values into ascending order. Once we get this vector, we can use it in the index notation for matrices to select rows in sequence to make the data frame sorted as desired. And this slide gives a summary of data structures we've introduced so far. They are organized by their dimensionality and whether they are homogeneous or heterogeneous. In other words, whether all contents be of the same type or the contents can be of different types. You may wonder which cell factors should belong. Yes, it should be put along with vector in the first cell. The last slide summarizes all operators we've introduced so far and their precedence. So that's all for the data structure unit of this course. We'll start our discussion on ASK control structures next time.